So all of chapter 4 is about vector spaces. And what we're doing is we're generalizing vector spaces and generalizing what we mean when we talk about a vector. And so we're differentiating, not like in calculus, we're differentiating between a general vector space and Rn. And here's why we don't really need to do that. Any vector space is just a coordinate map away from Rn. If you're dealing with a vector space, it looks like Rn. It's isomorphic to Rn. So here's what I mean. We talked earlier about P, oops, I spelled P wrong. That's not good. We have this double bar P and subscript 2 is a set of all polynomials of degree less than or equal to 2. So everything that looks like a polynomial of degree less than or equal to 2. One of the axioms in when we look at a vector space, the 10 vector space axioms, scroll all the way up, there we go. If I add two polynomials of degree less than or equal to 2, I will get a polynomial of degree less than or equal to 2. Because I'm adding polynomials, I can't get a degree more than 2. If I add polynomials, I'm just using the addition of real numbers and like terms. So that's going to be commutative and associative. 0 will serve as my 0 polynomial, because 0 plus any polynomial will give me the original polynomial. If I take the opposite of each of the coefficients of a polynomial, I'll get the opposite of the polynomial, so they will add up to 0, and so on. We can check that this is a vector space by running through the 10 axioms. Since we're describing a vector space, it must be the span of a set of vectors, and so we must be able to establish a basis for this vector space. So a basis, the standard basis for P2 is 1 t and t squared. The standard basis for P2 is 1 t and t squared, because every polynomial of degree less than or equal to 2 is a linear combination of these 3 polynomials in R2. So this is the easiest basis to use. That's why this is the standard basis. So if I look at a polynomial, P of t is equal to 2 minus 3t plus 5t squared. This is a linear combination of the vectors in the basis. It's 2 times the first vector. It's 2 times 1 minus 3 times t plus 5 times t squared. So if I call this basis B, this is the basis B, I can write the coordinates of P relative to the basis B as 2, -3, 5. So through this coordinate map, we've made P2 look just like R3. Everything in P2 can be made to look like a vector in R3. Everything in R3 can be made to look like a vector in P2. So if I have some other vector, if let's say the coordinates of Q relative to B were 4, -1, and -7, then Q as a polynomial would just be 4 times the first vector minus 1 times the second vector minus 7 times the third vector. 4 minus t minus 7t squared. That'll be the vector q of t. Oops, scroll. So we're using a coordinate map to make P2 look like R3. So the dimension of P2 is 3. That's why we can make it look like R3. Any questions? Let me introduce another kind of vector space, a vector space of matrices. So, for example, M sub 2 by 2 is the set of all matrices this will be the set of all matrices, all 2 by 2 matrices. Yikes. So M 2 by 2 can be the set of all 2 by 2 matrices. The standard basis for M 2 by 2, there are 4 entries in a 2 by 2 matrix. So I'll have to say 1, 0, 0, 0. Then I could go by rows. So 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Every matrix that is 2 by 2 is a unique linear combination of these 4 matrices. We can't get away with fewer, any more would be extra. So M 2 by 2 is a 4-dimensional vector space because there are 4 vectors in a matrix. If I have a matrix A, if the matrix A is 2 by rows, 2, negative 3, 4, 5, I can write this as a unique linear combination of the 4 vectors in the standard basis for M 2 by 2. I can say it's 2 times this the first matrix, 1, 0, 0, 0, minus 3 times the second matrix, 0, 1, 0, 0, plus 4 times the third matrix, 0, 0, 1, 0, plus 5 times the fourth matrix, 0, 0, 0, 1. And so if I name this matrix B, as I tend to name them B, then the coordinates of A, the coordinates of A relative to basis B are 2, negative 3, 4, 5. And now I've made M 2 by 2, where the things are all 2 by 2 matrices. I've made M 2 by 2 look like R4 with a coordinate map. We used a coordinate map to make the M 2 by 2 look like R4. M 2 by 2 is a 4-dimensional vector space. Notice that A is in M 2 by 2 because it's a 2 by 2 matrix. The coordinates of A relative to B are 2, negative 3, 4, 5. That is in R4. The coordinates will be in a different place, or could be in a different place, a different space than the vector itself. So that's what we care about in chapter 4, writing down coordinates. Then we want to just adapt this to other bases. These are the standard bases for these 2 spaces. And we could have some strange weirdo bases for these same vector spaces. So for example, let me pull up a weirdo base. Oops, that's not. Let's see, I think it's in 4. So all the stuff that we've talked about up to this point, this is like the first 4 sections of chapter 4. But all of it's very familiar, and it's really just down to organizing things, organizing a vector space as a basis so that we can make a coordinate map. So one of the, let's see, no, I want 5. 5 is basis. So first 5, we've done 5. Oops, nope, basis 6. We've done 6 sections of R4 of chapter 4, not R4, chapter 4. So if we go down to the problems in chapter 6, do we know how to do these problems? Oh yeah, we know how to do those problems too. Where did that basis go? Yeah. So sorry, I moved myself off of where I wanted to look.